Welcome back. In the last lecture, we have seen the history of periodic table. But in the line of periodic table, there are two important men. Demetrius Mendeleev, who is the father of periodic table, and the other man that takes the modern periodic law. Now, after their work, it is not necessary for us to look at elements in periodic table and look into the details of properties that they are talking about. In this lecture, we want to look at this hierarchy. Every element consists of atoms. All atoms made up of nucleon. Inside the nucleon, there are proton and neutron, as well as shell, which is called energy level. On the shell, there are orbits, and inside the orbits are electrons. And we know that this orbit that we are talking about, it is the action of wave motion movement of electron. Now, there are many scientists that contribute to development of where electron is in an atom before we can finally establish the structure of an atom to be planetary nature. Although, at the end of the work of Nebo, the planetary structure of atom has been fully established, but the true nature of electron has not. This is what brings us to the field of quantum theory. The work of all scientists, a line of quantum, the Heisenberg, the Schrödinger, and the Bragg, all these people that come together to establish all these laws. They are very, very important. Now, another things that we need to look at in this place, it is the nature of those things that we need to look at in detail. Did you remember that the atom is like this? But note, the shell here, the electron here, is not really depicting our orbital structure. It's only showing the shell structure with electrons around the shell. And here you can see the orbits that are on them. So this is 1s, so there's no 1p. This is 2s, 2p, there is no 2d. This is 3s, 3p, 3d, there is no 3f. This is 4s, 4p, 4d, 4, like that. 4f, there is no 4g. And from that, we know that the maximum electron in per shell is equal to what? 2n raised to power 2, where n is the shell number. And you can see the KLMN notation. So, for each of the orbits that we have, they have particular structure. These are the S's. The S1 is small compared to S2, S2 is small compared to S3, and they are what? Spherical shape. These are P's, which are dumbbell, the one along X, this one along Y, this one along Z. That makes it to have 3 suborbital structure. Why this is D have 5 suborbital structure. DZ, the one that is along the line of Z square, the one that is along the line of X and Y, we have X square, Y square, the one that is along the line of what? Y, and in between X and Y. In between X and Y, you can see that this is X, this is Y, so there is an orbital between X and Y. There's another orbital between Y and Z. Here you can see this is Z, this is a line, this should be line X. So we have orbital in between the line. What you will note in this structure is that most of the orbitals are either for directly or in between. So when they are between here, like this, we have x squared minus y squared, we have xy, we have dyz, we have dxy. And these are the 5D orbital structure. For UTME students, you will need this particular thing here. So it is necessary for you to know the type of suborbital that exists in D orbits. Now, the actual location of electron was actually established with wave function. And inside the wave function, what we are talking about wave is that it is a structure, and it is structured in somehow But most of wave that we are seeing in real life are mechanical wave. Most of electronics wave, we see them with our tools. You know that wave is actually representing some certain level of motion, and some structure in nature can resemble wave in actual sense. If you look at this volume regulating button here, you will see that the whole structure represents wave structure. And by drawing them out, you will be able to see that they are actually wave in nature. You look at this. This is 0 decibel. That is 0 decibel level. So the one that fall below is 0, they are below negative, while the one that fall above 0 are the positive. And if you could look at this wave, this one fall below 0, that is for this one here. This one fall above 0, that is for this one here. This one fall below 0, that is for this one here. This one fall above 0, that is for this one here. While this one fall below 0, this is for this one here. You can say that the whole structure of this particular object here actually represents a wave nature. So therefore, there are some structure in nature that if you see them, the way they are aligned, you will be able to see that they actually represent a wave. And I want you to remember, because I know that they taught you in mathematics during the course of variation, if you could remember very well, that for every equation, there is graphical representation. That is, this line that you see here is actually a graph of subset of equation. And that set of equation can be what? Can be function of sine wave, can be function of cos, can be function of exponential wave. So it depends on the nature of the wave that will enable you to know that this is what the wave is look like. And each wave have their own characteristics, but that is not what we are actually, that's not what we are actually interested in now. Now, every wave have definite function, and their function is known as what? Y is equal to what? Sine theta. This sine theta, it is the angular rotation of the wave. Why this Y? It is the amplitude that each wave have reached at a particular point in time. That vertical line is known as Y's. So this Y is telling us the vertical amplitude, the vertical height this particular wave are thrown. So that is to say, to know the vertical height at a particular point, we need to know the word angular rotation of the wave. But in physics, this theta has been manipulated to a very large extent to include both time and space. Are you getting me now? That is to say, the vertical height of any wave at a particular point, it is the function of what? Time and space, which is x-axis. So therefore, then I cannot say that something like this, y is equal to what? Sine. For now, just write it. I know that you don't know anything about this, but we are going to try to trash it out. Are you getting me now? Angular wave plus minus what we call this phi. This phi is a function of particular thing, and that thing is what we call distance. Most of the time, it is written as what? Maybe 2 pi fx, if I'm not doing mistake, because there are some things that we need to show in this scenario to actually let us arrive at particular equation. So here, this function is telling you that the height that the height of the wave at a particular point in time will be determined on the time, as well as what at the horizontal distance that the wave has gone through. In this case, now this is the wave function, and you know that during the course of line of history of discovering the position of electron by a lot of scientists, the guy that proposed that, you know that from the work of Niebel, you could remember that he said that electron, they are on the what? They are on the energy level like that. They do not emit any energy spontaneously. But if you give them energy, they will excite to next energy level, and they will never stay at that place permanently. They will also return to where they are, and the energy that they have absorbed, they will release it in form of photon. That is to say, photon is released when electron is relaxing coming from higher energy level to the lower energy level. But another man come, he said that no, electron does not just wait like that. They don't just be like that in the moving around the orbit like that. During the motion, they exhibit what we call wave-like characteristics motion. Are you getting me? They exhibit what? Wave-like characteristics motion. And from this aspect, this is where Erwin Schrödinger pick it up. That, wow, if electron could have these wave-like characteristics in nature, we can use the characteristics of this wave to predict everything about the nature of electron and as well as their property like energy level where they belong to. So the work of Erwin Schrödinger was to use the property of wave, which is the wave function, to predict the kinetic energy as well as potential energy of electron in particular energy level. And that wave function, instead of using y, the guy used this particular sign. Instead of using y, he used this particular sign to represent wave function. He now tell you that the energy of the wave function can be determined, that each wave function can have particular kinetic energy and potential energy. So by doing that, they manipulate some set of equations which beyond the scope of this course. I cannot teach O level as well as UTME level, but I cannot teach you to O level as well as UTME level. But A level, it is a course that we must teach in details. And in that course, we are going to explain everything about that wave, how that energy, what are the characteristics of things that they have discovered, what is the meaning of this wave, what is the meaning of each tone in a particular wave structure, how this tone actually come to represent each of this orbital energy or suborbital structure. So therefore, that's all about that. You could remember that during the course of our experiment, to determine the energy level where the electron is in a particular atom. Our problem is electron, because it's one of the most fundamental things that we need to study in chemistry very well. So in order to determine the energy level, we have told ourselves what Bohr have done so far. Energy level was revealed by what? Emission spectra from the atom of elements, showing by what? Showing by Bohr, picturing the discontinuous spectra. What is the meaning of continuous and discontinuous spectra? The image that you are looking here is a continuous spectra. You can see that one light runs into another light without any gap in between. But look at this one here. Look at this one. You can see the band. You can see a band here. That band is around what? 410.1 nanometer. You can see another band here. You can see that each band stands distinctly. They don't run into one another. This type of display is called discontinuous wave function. And I must let you know, each light and dark band actually represents a wave structure. Are you getting me? It represents a wave structure. The way you see the light, it is the way we have maximum amplitude. Yes, that is something like this. If you have a wave like this, all this region here, there are regions where you find that particular light. But all other region, there are regions where you don't have light. But in order to simplify that, we know that for this kind of way to emit, we must see what we call standing wave. For every standing wave, there are two waves moving in opposite direction. One cancels out the effect of other in exact sense. So this point, at the point of darkness, where the amplitude is cut to 0, but here, where you see the maximum light, this is the way you see the light structure, where the amplitude is maximum. Here there is light, here there is darkness. So that is about how the wave is used to depict this particular light spectrum. And you can see there are 4 bands here. Band at 410.1, band at 434.1, band at 480.1, and band at 656.3 nanometer. So this is how they predicted that, okay, by looking into this particular number of band, this band could represent to the number of energy level that is present in an atom. But there are some emissions that it cannot be seen with our naked eyes. So from there, this is the actual spectral image for hydrogen. This is spectral image for helium. This is spectral image for iron. You can look at it and look at the number of energy level accumulation along the spectrum like that. Yes, this particular picture, we use it to depict that the higher the number of shell, the bigger the atom. You can see as the shell number increases, what happens? The atomic sizes and atomic radius become increases like that. There are some things that we are going to still say about these things, so we are still going to refer to this page in later lecture. So this is our periodic table. These are elements, and we have explained their architecture and structure in our previous lecture, but you should know that the periodic table is arrangement of elements in rows and columns. So this is the basic first 20 elements that every student needs to know in periodic table. With respect to what I'm saying here, represents something like it represents something in nature. So this is 1, that is 1 electron. This is 2 electron. This is 2 electron in first energy level. This is 1 electron in second energy level. So we have their electronic configuration. So this is 2H3 for what? Aluminium. So this is the electron configuration. We also have a beta structure as well as other structure. So electronic configuration now. We have 3 types of electronic configuration. We have ground state, we have excited state, and ionization state. And why are we having excitation state? We have excitation state in order to have what we call stable rule configuration. We want to establish, we want to make sure that every atom want to make sure that they have their stable electronic configuration. Releasing stable electrical configuration here doesn't mean that they will necessarily fill up their atom shell. No. There is levels of stability in atom. So if an atom have 2 sets of stability, it will prefer to take up the most stable structure. That's what we are trying to tell ourselves here. So we talk about electronic configuration, which is followed by Aufbau rule, Pauli exclusion principle, Hunt rule, and stability rule. If you look at them with respect to what we have done in the past lecture. And we say that there is another thing that we need to look at, because you need to know the energy order of the orbitals. That is to say, orbitals are arranged in order of energy level that they have. What we are saying here is that the higher the energy, the lower the stability. You know that. If you don't know, let me tell you. Let's assume that your parents intentionally starve you. They don't give you food and drink for 1 week. I am so sure all the strength that you used to walk to your school will not be there. If they leave you in a room, you are going to be in that room for all days. That is to say, there is no energy in you, and your rate of movement from one place to another has decreased. That make you stable in that room because of the fact that you don't have food. So the lower the energy, the higher the what? The stability. But if they give you food, they give you rice, they give you chicken, they give you turkey, you will now begin to go from one side to another. Mommy, come and see Mama Bola, they are fighting. What concerns you? It is because you have an energy that makes you to go from one place to another. If you don't have that energy, you will be stable. There won't be anything concern you with anybody. So use this scenario to note that the higher your energy, the lower the stability. And the lower your energy, the higher the stability. So therefore, we want to see the energy increasing order of the orbital shell. This is the increasing order of energy of our orbit. 1s is lower compared to 2s. 2s is lower compared to 2p. So 7p is the one with the highest energy level, and it is the less stable orbit in nature. So therefore, if you have too much unstable orbit in an atom, that atom will be an unstable atom because it consists of too much unstable orbit. Are you getting me now? So therefore, any unstable atom will have higher rate of reactivity. So this is at the first 20 elements as well as electronic configuration of what they have. Please, they are very, very important. So there are something that I really want to extract here, but for now, I don't know, maybe, okay, let me try to tell you something about this page. It would be very beautiful for me if I can see the orbital diagram instead of electronic configuration. If I can see the orbital diagram of electronic configuration. This one is what? 1. This one is what? 2. Are you getting me? And they are both what? They are both 1s. But this one is what? 1s2. Because helium is what? 1s2. And the next one is what? 2s1. 1s2, 2x1. So this is 1x, 2. This is what? 2s1. So by looking at the energy level, this is at energy level 1, this is at energy level 2. This is the outermost shell electron, which is known as what? Valence shell electron. So this is 1s1, not, sorry, this is 2x1, please. This is 2x1. Are you getting me? Now, for this guy here, which is beryllium, it is what? 1s2, 2s2. And you should be able to draw the orbit like that. So let me clear the board so that I can have more space to write for the other element. Now, let us look at boron. If you look at the boron, the second orbit now is not empty. Second orbit here is empty. That's the reason why we don't show that 2p. So here we have 2p 0 because it does not contain any electron. So if it is 0, we don't write it out. Are you getting me now? But in the case of our in case of our boron, we can say that the 2p1 is not empty. Look at this. What are we having here? We are having 1s2. Is that clear? We are having 2s2. Okay, we are also having 2p1. We are having 2p1. So this one is 2s and this one is 2p. The meaning is that these two orbits here, they are the outermost shell orbits, and they are all present in the same orbit. Excited state electronic configuration. Listen. If they ask you to write excited state electronic configuration, what will happen is that one electron from these 2s will excited into this one here. The electronic configuration will now become what? 1s2, 2s1, 2p2. That is what? Excitation state. That is, one electron will excite from this place to this place. Excitation will only take place if there is pair of electron in one and there is empty room in another. There is empty room here. If this one is just single electron, if it is not pair, excitation is not going to occur. Please note very well. For excitation electronic configuration, this is when you move an electron from the pair electron into an empty orbit. Are you getting me? But if they ask you to write what we call ionization state electron, for example, look at boron. It has 3 electrons in the outermost shell. That is to say, the electron that is in the outermost shell are 3. So you will knock them out one after the other. If you knock out the first electron here, the electronic configuration will become what? 1s2, 2s2. If you knock out the second one, it will become 1s2, 2s1. Are you getting me? That's the difference between excitation electronic configuration and what? Ionization electronic configuration. It goes like that. So here, we are looking at some element diagram state electronic configuration, the excited state electronic configuration, as well as first, second, and third ionization energy. So ionization electronic configuration, sorry. Now, in this case, Please, I want you to note this table very well and note your differences that you've seen so far in the table, but I will to show you some things. Look at aluminium. This is the ground state electronic configuration. 1s2, 2x2, 2p6, please. This one are power of this, 3x2 and 3p1. Excited state electronic configuration. It may upon excitation may be possible or not possible, depending on maybe there is a pair of electrons that we can promote. Are you getting me? So here, excited state electronic configuration, if we look at this is what? 2p. So which one are the outermost shell? 3 are the outermost shell. So we have 3s2 and 2p1 as the outermost shell electron. So one electron will be promoted from 3s2 to what? 3p1. It will now become what? 3s1 and 3p2. For the ionization, knocking out the first electron, knocking out the second electron, knocking out the third electron. So in this case, ionization energy took the what? Ground state electronic configuration. If you knock out this electron, this one will become what? P is 0. As a result of that, if P is equal to 0, you don't need to write it, you remove it out of the system. So the same thing is applicable to all other. From this case, we can now see that if electron is excited or ionized, their electronic configuration can be equal. Are you getting me? For example, look at sodium, magnesium ion, and aluminum ion. They are isoelectronic. The meaning is that they have the same number of electrons. They have the same number of electrons. Elements that have the same number of electrons are called isoelectronics. Now, tendencies to lose or gain electron depend on the amount of energy, ionization or electron affinity that will be required to attain stable electronic configuration. Recall patterns in quantum number. Now, I want to show you something. Let us remove this one first and focus at this. Let us remove this one first. Let us focus at this. Let us focus at this. You know that in periodic table, some element has been predicted to be metal or non-metal. Metal has ability to lose electron. Non-metal have ability to gain electron. But the tendency to lose electron or gain it, how are you going to know? I will show you here. I want you to look at period 2 element, sodium and chlorine. Let us look at their electronic configuration. This one is what? 1s2, 2x2, 2p6, 3x2. This is 3p1. This is 3p1. So we have 3p1. This guy is what? 1s2, 2x2, 2p6, 3p, 1s2, 2x2, 2p6, 3x2, and 3p5. Now, for these two atoms here, they are in where, if I'm not mistaken, they should be in period 3. So this one has achieved its own full electronic configuration. Are you getting me? It has achieved its own 2 electrons in this one, then 1 electron in this one. Now you will see what I'm talking about, please. But this one, what happened? 2 electrons here, 8 electrons here, eight electron here, why there is 7 electron here. 7 electron here. Seven electrons here. Now, I want you to look at this periodic table here. These two atoms here, they are in the period 3. Automatically, they should try to obtain what we call 18 electronic configuration stability. But look at them. In order to achieve this 18 electronic stability, what do they need to do? This one, in order to achieve that, has to gain about 17 electrons. This one has to gain about much more electron. It's not going to be possible. So this electronic configuration is too far for them to reach. They will now look at the next stable electronic configuration, which is what? 8. 8 is very easy for them to attain because they won't want to spend much more energy to attain that electronic configuration. In order to have 8 electrons in this place, we need to add just only 1 electron. Or we had only 1 electron, or all these 7 electrons, we throw them away. So if we throw all these 7 electrons away, what happens? This shell will disappear and they will have only 8 electrons, which is octet stability. Now, start to compare. In sodium, in order to achieve that octet stability, is either we add 7 electrons to this, plus 7 electrons, or we remove this 1 electron. Which one is easy? The same amount of energy is expended in adding and removing an electron. In order to achieve stability, sodium here will prefer losing this particular 1 electron. By doing that, it will obtain its own octet stability by just losing 1 electron. But this guy here, it will prefer gaining 1 electron in order to achieve its own octet stability at the 3rd shell. So therefore, because of the prevalence of losing and gaining of electron, we are able to classify elements as what? Metal or non-metal. In this scenario, what you are saying is that sodium will prefer to lose an electron, so therefore it's a metal, while chlorine will prefer to gain an electron, so therefore it is non-metal, because of the amount of energy that will be expended during gaining and losing of electrons. Now, another thing that we want to talk about here, is about electronic quantum number. And it is very important to make mention to this because some students are telling me that they don't understand the patterns in that quantum number. I have told you, but one of the simplest way you can go about quantum number is to draw a table. Is to draw a what? A table. So by drawing your table, what do you want to indicate? Let me rub the board so that you can see. What do you want to indicate on the table? You want to indicate energy level, which is what? Principal quantum number. You want to indicate the orbit, which is what? Azimuthal quantum number. You want to indicate the suborbit, which is what? Magnetic quantum number. You want to indicate the spin, which is what? Spin quantum number. This is magnetic, this is spin. So by drawing this table, you should not have any problem writing out your 4 quantum number. And I will illustrate it with very simple example. But I must let you know that the question vary. You must understand your question first before you answer it. But this question will cover the maximum level of any question that you may likely want to answer. So now Let's assume that you have sodium. You want to write the quantum number of sodium. Sodium is in period 3. That is to say, it has 3 shells. So you are going to write for the first energy level, second energy level, and third energy level. So this is what n is equal to 1. This is n is equal to 2. This is n is equal to 3. So the energy level. So for each of these energy level, you are going to indicate the what? The spin number, the azimuthal number. This one here, you know, remember that the allowed value for azimuthal is what? N minus 1. So this one is 0. Are you getting me? For 0, that is to say, energy level 1 will only have what? S orbit. But this one is what? Is 1, but it's not ordinary 1. If it is 1, it is coming from 0, then get it to what? Get it to 1. So for the 0, you will write the orbit, which is what? X. For the 1, what are you going to write? You are going to write P. Are you getting me? That is to say, for the second energy level, there is S and P energy level. For the third energy level, what you have is what? 0, 1, and what? And 2. Make sure that you space out the number. Are you getting me? So for the 0, it is X. For this 1, it's equal to what? P. For the 2, it's equal to what? It's equal to what? It's equal to D. Thank you. For the 2, it's equal to D. So now, for each of these S, you are going to write the spin. Here is what? 2 electron. And the range of the what? Magnet is what? Minus L to what? To plus L. This one is 0 in value. Are you getting me now? Because it's from minus L to L. So L is 0 here. It's also 0 here. This one is 0. Why this one is what? From minus L to plus L. This is what? 1. Minus 1, comma, is 0, comma, 1. Why this one is what? Is 0. Yes. Minus 1, comma, is 0, comma, what? Plus 1, comma, plus 1. Why this one is what? Minus 2, minus 1, yes, is 0, yes, plus 1, you will write plus 1, to what? To plus 2. So for the spin energy level, what do we have? So the first energy level has 2 electrons in opposite spin. So we have up spin and what? Down spin. So it's going to be what? Plus or minus what? 1 over 2. Up spin, down spin. For this one, it is sp2. So it has its own 2 electrons. It is what? Plus or minus what? Minus half. We have 2 pieces. So this one will have, this one here, minus 1 will have plus or minus half. While the one in the middle will have plus or minus half. While the one here will have what we call plus or minus 1 half. Sorry. So you put the comma to separate them like that. Now, in this case here, what we have is only what? 3p1. That is to say, all of these shells are not occupied. For 3p1, here, what I'm going to have is only what? Plus downspin. Only half. Only half. We are not going to use minus. We are going to, so if it is downspin, it's going to be what? Minus half. Are you getting me? Minus half. Minus half. So it is not plus or minus half because it is not up to 2 electrons, just only 1. In that case, these 2 shells here that does not contain electrons, you are going to remove them from the quantum number of sodium. So this table actually shows the quantum number of sodium. So if you want to write quantum number for any element, remember how to draw this particular table. On the table, distribute the shell and distribute their L. I get me, identify their value and the orbit. So for M, remember the value for the M for each of the sub-orbits, then write the spin for the electron inside the orbit. So, according to several electronic configurations, an atom can be diamagnetic or paramagnetic or ferromagnetic. And this property depends on electronic configuration. If all the electrons appeared in opposite spin, that atom is said to be what? Diamagnetic. It does not have any magnetic property. Example of this element in this one, this particular D element, you can see all the electrons appeared in opposite spin. So this element here is diamagnetic. It does not have any particular magnetic property. And paramagnetic, there will be one or more unpaired electron like this. This one is what? 2 unpaired electron. Let me take my red so that you understand what I'm saying. So this one here is 2 unpaired electron. This one here is also 2 unpaired electron. This one here is 3 unpaired electron. This one is 1 unpaired electron. This one is 3. This one is 4 unpaired electron. So this one will be the highest value of paramagnetic, followed by the 1, 3, followed by the 1, 2. So since there is unpaired electron, those atoms are what? Paramagnetic. But ferromagnetic will be like this. A ferromagnetic will contain all electron pair, but not in opposite spin. It will now be in the same spin. It's either up, up, or down, down. They will have very strong magnetic property. So this is electronic configuration of elements and their ion. And I choose this particular element, which is what? We have looked at first 20 elements. This is the first transition series. I want you to monitor the electronic configuration. But let me take your course through it before you actually say that I want to try to study them. This is electronic configuration of ground state. That is to say, in a neutral atom that does not possess a ion, this is the electronic configuration. Let us look at it. Every element in first transition series will have electronic configuration for what? Argon, followed by what? And you know that electronic configuration of argon, where does it stop? If you could remember, let's go back so that you will see what I'm talking about. Where is argon? This is our argon. This is argon. Look at argon. Argon have neon electronic configuration followed by what? 3s2 and what? 3p6. Where is neon electronic configuration? This is neon electronic configuration here. It has helium, and helium is just what? It's just 1s2. Helium is just 1s2. So this is 1s2, 2s2, 2p6, 3s2, 3p6. That is argon electronic configuration. So after argon electronic configuration, they will have 3d orbit followed by what? 4s. You can see that 3d comes before 4s in that electronic configuration. Please do not do the mistake. This is due to the fact that orbits are in order of energy content. The higher the energy, the slower the stability, and the more the lag will occur. That is to say, the orbit with lower energy will occur first before the orbit of higher energy. Let us show ourselves that orbital energy level. That reason why you need this particular diagram very well. You can see 1s2, 2s2, 2p2, 3s2, 3p2. You can see 4s2 come before 3d. If you look at this, 4 is greater than 3. Automatically, 3d is supposed to come before 4s. But experiments show us that 4s energy is lower compared to 3d energy. Are you getting me? Despite the fact there are some cases where we first of all feed electron into this. That's the reason why we say that electrons go into penultimate level, that is to into the inner shell in first transition series. That is to say, in transition series, there are some abnormality in their electronic configuration that is very different from first 20 elements. So now, I want you to know that for the first 20 elements, the principle of excitation to achieve the most stable electronic configuration is not applied. But in the case of first 20, in the case of the first transition series, something changed entirely. Something changed entirely. Look at chromium. I want you to look at chromium, this element here. Look at chromium. this element here. Look at the electronic configuration. Don't you think that this one here is supposed to be fully filled and this one should be empty? Yes, it should be like that. But what they note is that this element here is about to achieve single electron stability. So if all this electron is paired and this one is just only one, it will be stable compared to if these two electrons is here. Because of the lack of electron in this place, all this structure of orbit will not stable because this orbit will be clamoring for electron. But in this case, this one is nobody is clamoring for electron. So because of that, we need to look at which stable electronic configuration is possible nearby, at least to the level of 1 electron. Look at this. It is not applicable to this. This is because if you mistakenly promote 1 electron from this place to this place, you have introduced a more unstable state because this shell will be clamoring for its own electron. So because of the fact that the half field is not about to be achieved here, we don't promote that electron. You know that electron goes into orbit of lower energy before higher energy. And that's the reason why we first of all fill 4s before 3d. Are you getting me? Normally, all 4x orbits should contain two electrons. But because of the rule of stability, there are some excitation that will occur to some elements that are about to achieve single electron stability. Remember, the full field electronic configuration is more stable than half field electronic configuration. So, an half field electronic configuration is more stable than partial field. This guy here is partial field. So the orbit, these two orbits here, they are clamoring for electrons. So therefore, this orbit is very, very unstable. Why this one is stable? Automatically, chromium is more stable than vanadium. Are you getting me now? So chromium will be less reactive than vanadium with respect to this electronic configuration. The same thing is applicable to their ions. Just look at the state where it is about to achieve that particular electronic configuration. This is the ionization state electronic configuration. During the ionization state, they can remove the what? Look at it from the chromium. For chromium, this is our chromium, you see, in this case. So two electron has been removed here. While 1 electron has been removed here, that makes it what? Chromium 3 plus, because 3 electron has been removed. So there will be 3 protons that are lacking electrons. So this is everything about the nature of electron inside an atom. We have reminded ourselves, we have also reversed how to write quantum number for any element in periodic table. We have reversed the atomic history of discovery of electron and the de Broglie theory. You remember that guy, de Broglie? I know you still remember that de Broglie is the one that proposed that, okay, around a shell, electron have what we call wave-like property. That is the Broglie idea. And from de Broglie, Schrödinger come up that, okay, using this wave, we can determine the characteristics of the wave. We can determine the energy, we can determine the frequency, we can determine the kinetic potential energy as all other to know the location of the wave. But before Broglie, there is a one man called nearby that determined that, okay, there is electron orbiting around. This guy said that instead of them to be orbiting around in the elliptical path, they orbit around in the wave character path. Are you getting me? So this is everything about this today's lecture. We are going to continue in our next class. Thank you for listening. ABP.